Hi friends, ఈరోజు మనం Hertnell governor problems చూద్దాం. So look at here, a Hertnell governor having a central sleeve spring and two right angles of bell crank levers moves between 290 rpm and 330 rpm. సో రెండు స్పీడ్స్ ఇచ్చారు. ఇక్కడ బాల్స్ అనేవి రొటేట్ అవుతూ ఉంటాయి. అది కూడా ట్రయాంగులర్ షేప్లో ఎల్ షేప్లో ఉంటాయి. ఓకే, సో ఫర్ ఏ స్లీవ్ లిఫ్ట్ ఆఫ్ 15 mm, the sleeve arms governor axis sleeve arms and ball arms are 80 mm and 120 mm respectively. The levers are pivoted at 120 mm from the governor axis and mass of each ball is 2.5 kg. The ball arms are parallel to the governor arms at the lowest equilibrium speed. Determine first one, loads on the spring at the lowest and the highest equilibrium speeds and stiffness of the spring. Okay, this is the problem is given. So now we are going to see how to solve this one. Hertnell governor. So given data, N1 is equal to 290 rpm. That's called angular velocity is equal to 2 pi n by 60. So 2 into pi into 250 divided by 60. 290 is given. So that the answer is coming from 30.4 radians per seconds. And then now we are going to see N2 is equal to 310 is given. So omega 2 is equal to 2 pi n by 60. You can put 2, you can here also 1. Ten divided by 60. So that is the answer. It will come 32.5 radians per seconds. Okay, and h is given 15 mm, so that is equal to 0.015 meter. Y is given 80 mm, that is called 0.08 meter. So X is given, that is called 120 mm, so that is equal to 0.12 meter. And then R is given 120 mm, so that is called 0.12 meter. So M is given 2.5 kg. Okay, totally this is the given data. And now we are going to see here axis first, lowest position and highest position diagrams. So right hand, this is given for 90 degrees. This is R. So this is called B, and then this is called FC. R is equal to R1. There is no difference. So here is acting one force and here is acting one force. So this is called, we know very well, mg. And here to here is called x, that is equal to 120 mm. This is called y. We know very well, this is called governor axis. This is the angle is coming like this. Okay, and this is called mg plus s1 divided by 2. Okay, now we are going to highest position. So similarly, this is axis. And now I put it here, O point is there. This is B. This is FC2. This is having exactly 90 degrees. Okay. Then here is point, we take R. And then here to here distance is called H. That is equal to 15 mm. 15 mm is given. Okay, and then they put it here R2. So this is Y and this is X. Now here is coming from mg plus s2 divided by 2. Here to here distance is called R2. Here to here distance is called R1. This is axis O point, and now we are going to see in here X2. And here to here it will come X2. Okay, so this is the totally given data, and now here I put it governor axis. This is governor axis. Now here to here distance is there. This is called Y2 and this is 120 mm. This is fixed for both. Okay, and now A, this is lowest position, and now this is highest position. Okay, సో గివెన్ డేటా ప్రకారం మనం ఇప్పుడు యాక్చువల్గా ఎగ్జాక్ట్గా డయాగ్రామ్ అనేది డ్రా చేసుకుంటున్నాము. ఓకే, ఇప్పుడు అన్నోన్స్ ఏంటి అనేది ఇప్పుడు మనం ఫైండ్ అవుట్ చేద్దాం. సో దెన్ ఫస్ట్ వీఆర్ గోయింగ్ టు హియర్ లోడ్స్ ఆన్ ది స్ప్రింగ్. Loads on the spring at the lowest highest equilibrium speeds. Okay, so let S1 is equal to spring load at lowest equilibrium speed, and S2 is equal to spring load at highest equilibrium speed. Since the ball arms are parallel to governor axis at the lowest equilibrium speed, N1 is equal to 290 rpm. ఓకే, సో ఇక్కడ మనం చూసినట్లయితే పిక్చర్లో మనకి ఈ బాల్ అనేది యాక్సిస్ గవర్నర్ యాక్సిస్కి, ఇక్కడ చూసినట్లయితే గవర్నర్ యాక్సిస్కి ప్యారలల్గా ఉంది ఈ లివర్ అనేది. ఓకే, సో that the thing R is equal to R1, that is called 120 mm, that is 0.12 meter. So we know that centrifugal force at the minimum speed FC1 is equal to m into omega 1 whole square into R1. So then 2.5 into 0.12. So omega is 30.4 whole square into 0.12. Here we find out omega 1. Okay, we are going to substitute here simply and calculate this. We'll get the answer in here, 277 newtons approximately. Now let us find the radius of rotation at the highest equilibrium speed, that is coming from N2, is equal to 310 rpm. So the position of ball and sleeve arm at the highest equilibrium speed is shown. Let R2, then here R2, okay, R2 is equal to radius of rotation at N2 is equal to 310 rpm. So then here H is equal to R2 minus R1 y by x. Okay, so R2 is equal to R1 plus H y by x. So then 1.12 plus 0.015, 0.17 divided by 0.08, that is equal to 0.1425 meters approximately. So therefore centrifugal force at maximum speed FC2 is equal to m into omega square into R. Then 2.5 into 32.5 whole square. Here omega 2 is there, the value 32.5 radians per second square into 0.1425. So that is equal to 376 newtons. So neglecting the oblique effect of arm and the moment due to the weight of the balls, we have for lowest position, so taking moments here, m into g plus S1, that is equal to 2 FC1 into x by y. So that is equal to 2 into 277 into 0.12 divided by 0.08. So that is equal to 831 newtons. Okay, so then S1 is equal to 831 newtons. Yeah, okay. And then now we are going to see highest position. Similarly, highest position is called S2 is equal to 2 FC2 into X by Y. Okay, that is equal to 2 into 376 into 0.12 divided by 0.08. That is equal to 1128 newtons. So S2 is equal to 1128 newtons. Answer is that. Okay. Then we are going to find second thing is stiffness of the spring. So then we know the stiffness of the spring S is equal to S2 minus S1 divided by H. So 1128 minus 831 divided by H is 15. Then here we find out 19.8 Newton per mm is the stiffness of the spring, Newton per mm. Okay, this is the procedure to solve the problem. And now here we will see another one is in here. So look at in here, in a spring loaded Hertnell type governor, the extreme radii of rotation, the balls are 80 mm and 120 mm. The ball arm and the sleeve arm of the bell crank lever are equal in length. The mass of each ball is 2 kg. If the speeds at the two extreme positions are 400 and 420 rpm. Find first one, the initial compression of the central spring, and second one, the spring constant. So in previous problem, like as the previous problem, so then here we are see problem number 2 solution. So first I am going to written given R1 is equal to 80 mm, that is called 0.08 meter. Then R2 is equal to 120 mm, so that is equal to 0.12 meter. So X is equal to Y. Then M is equal to 2 kg and N1 is equal to 400 rpm is given. So 400 rpm or omega 1 is equal to 2 into pi omega 1 whole square into r. Then 2 into pi into 400 square into 0.12. So then that is equal to 40. Wait. What happened? So omega 1 is equal to 2 pi n by 60. Then 2 into pi into 400 divided by 60. Then here we are going to calculate this. We find 41.9 radians per second approximately. And then here we are going to see N2 is equal to 420 rpm. Then omega 2 is equal to 2 pi N2 by 60. So 2 into pi into N2 is equal to 420, then 60. So this answer it will come around 44 radians per second. This is the given data for this. So now we are going to see in here initial compression of the central spring. So we know that the centrifugal force at the minimum speed Fc1 is equal to m into omega 1 whole square into r1, then 2 into 141.9 whole square into 0.08, then this is equal to 281 newtons. The centrifugal force at maximum speed Fc2 is equal to omega 2 square into r2. Then here 2 into 44 whole square into 0.12. Then that is equal to 465 newtons. So S1 is equal to spring force of the minimum speed and S2 is equal to spring force at the maximum. So then I can write here for clarification, spring force at the minimum speed and S2 is equal to spring force at the maximum speed. So we know that for minimum position m into g plus s1 divided by 2 is, it will come right here, fc1 into x divided by y. This is the standard equation. So then s1 is equal to 2 into fc1, so 2 into 281, so that is equal to newtons. Okay, so similarly we are going to see here maximum spring S2, that is equal to Fc2 into x by y. Then S2 is equal to 2 Fc2. Then here 2 into 465. So that it will come 930 newtons. Now we know that lift of sleeve H is equal to R2 minus R1 y by x. That is equal to R2 minus R1 is equal to 120 minus 80, then it is coming from 40 mm. So therefore stiffness of the spring, that S is equal to S2 minus S1 divided by H. Then here 930 minus 562 divided by 40. 9.2 Newton mm. So now here we are going to know about initial compression of the central spring. So then that is equal to S1 divided by S. So 562 divided by 9.2, that is equal to 61 mm is the answer. And now then we are going to find out spring constant. We have calculated above that the spring constant or stiffness of the spring S is equal to 9.2 Newton per mm. So this is the final answer. Okay. So this is the procedure to solve the Hertnell governor problems. Okay. Thank you.